Inside every single living thing, from a tiny bacterium all the way up to you, there's this incredible drama playing out nonstop. It's a story about these microscopic machines that, well, they power everything. And it all boils down to one single thing: getting the perfect shape. So let's dive into this amazing world of molecular origami. So this is the big mystery we're going to unravel. How does a totally useless string of building blocks manage to fold itself into a complex, life-giving machine? And on the flip side, what happens when that process goes horribly, horribly wrong? The answer is it's a journey of epic proportions, right down at the molecular level. Every great story needs a hero, right? Well, ours is the protein. But it doesn't start out as a hero. No. It begins as just a simple, long chain, a polypeptide, with this incredibly important destiny it has to fulfill. This is its origin story. Okay, so picture this. This is the very first moment of our protein's life. Deep inside a cellular factory called the ribosome, a set of instructions is being read, and these little building blocks, amino acids, are getting linked together, one after another. What you end up with is this long, floppy chain. It's full of potential for sure, but right now, it's completely useless. Its entire quest is to fold. And this is the absolute key, the most important point. A protein's job isn't just about what it's made of. It's all about the crazy complex three-dimensional shape it folds into. Without that specific structure, it's just a piece of string. To literally come alive and do its job, it has to perform this perfect act of origami. So how in the world does it find that one perfect shape? I mean, this is not a simple task. The protein is facing an almost unimaginable number of possibilities. It's like it has to navigate this treacherous, invisible gauntlet. And this brings us to something called Leventhal's paradox, which basically highlights how impossible this whole thing should be. You see, for even a small protein, the number of ways it could potentially fold is just astronomical. If it tried to find the right one by just randomly sampling every single option one by one, well, it would take longer than the entire age of the universe. Life just couldn't exist. And just to give you a sense of scale, look at this number. This is an estimate for the number of possible shapes for a small protein, just 100 amino acids long. That's almost a 3 with 94 zeros after it. I mean, to put that in perspective, scientists estimate there are only about 10 to the 80 atoms in the entire known universe. It's just a mind-shattering number. So, as Cyrus Leventhal himself figured, this means folding can't possibly be a random search. It's just not possible. There has to be some kind of pathway, a guided process that funnels the protein to its destination super, super fast. We're talking microseconds to seconds. And this beautiful diagram shows the solution. It's called the folding funnel. Instead of a random search, the protein is guided by physics. Think of it like a ball rolling down a really bumpy hill. At the very top, where the funnel is wide, that's the unfolded high-energy protein. It just sort of tumbles downhill, pulled by physical forces, which rapidly narrows down its options until it finally settles into its one perfect, low-energy shape at the very bottom. But, and this is important, see those little dips and valleys on the sides of the funnel? Those are traps. Those are places where a protein can get stuck in the wrong shape. And getting stuck, that's where our hero's journey can take a really dark turn. What happens when a protein doesn't make it to the bottom of the funnel? What if it gets trapped and folds into the wrong shape? Well, this is where tiny cellular mistakes can become absolutely catastrophic diseases. This is the devastating real-world result. Mad cow disease is caused by literally nothing more than a protein folding into the wrong shape. And this isn't some minor error. It's a fatal flaw that can completely destroy a nervous system, turning healthy brain tissue into this spongy, useless mass. The villain of this story is something called a prion. Now, a prion isn't a virus, it's not a bacteria, it's one of the body's own proteins, just misfolded into a toxic, infectious shape. And this corrupted version, it acts like a seed, triggering a terrifying chain reaction that corrupts other healthy proteins. The way this works is just chillingly simple. The normal, healthy version of the protein is called PRPC. But when it bumps into a misfolded, toxic prion version called PRPSC, the prion acts like a template, and it forces the healthy protein to change its shape into the dangerous one. These newly corrupted proteins then go on and convert others, and they all start clumping together. It's this unstoppable chain reaction that causes all that devastating damage. It's like a molecular zombie apocalypse. And it's not just some rare prion disease. This whole idea of misfolded proteins clumping together is now understood to be at the heart of many of our most devastating brain disorders. Alzheimer's, Parkinson's, Huntington's, they all involve specific proteins that fail their folding quest and end up forming these toxic aggregates in the brain. Okay, but the cell is not defenseless. I mean, with stakes this high, you'd better believe it's evolved some really elegant systems to help our hero protein stay on the right path. It's got guides for the journey and a full-on cleanup crew for when things go wrong. So meet the first line of defense, molecular chaperones, like this one called HSP70. As our new protein is being born, literally coming out of the ribosome, it's super vulnerable. HSP70 acts like a bodyguard. It grabs onto the unfolded chain and shields it, preventing it from getting all sticky and clumping together before it's even fully built. Then, once the whole chain is complete, the chaperone lets go, giving the protein a clean slate to fold up correctly. Right, but even with these guides, mistakes still happen. A protein can still get stuck in one of those energy traps on the side of the folding funnel. So what does the cell do with these failures? It can't just leave dangerous misfolded junk lying around. This is where the cleanup crew comes in. And the cell's quality control system has two main parts. First, on the left, you see this little molecule called ubiquitin. Think of it as a molecular kick-me sign, or a tag for disposal. Then on the right, you have the proteasome, this big barrel-shaped machine that is basically the cell's paper shredder. So the process is basically a two-step system. When the cell finds a misfolded protein, it slaps a whole chain of these ubiquitin molecules onto it. That chain is a signal that says, hey, destroy this thing. The proteasome recognizes that tag, grabs the doomed protein, yanks it inside, and just chops it to pieces. It breaks it down into its basic amino acids, which can then be recycled to build new healthy proteins. It's an unbelievably efficient system for taking out the trash. So after all of this, we've built this entire story around one central idea, right? A protein must find a single, perfect, stable shape to do its job. But what if that's not the whole story? What if I told you there are proteins that are actually meant to be disordered, that are supposed to be floppy and unstructured? It turns out the cell is full of them. They're called intrinsically disordered proteins, and their lack of a fixed shape is the actual key to their function. It's this fascinating plot twist that completely flips the script on everything we thought we knew, and it shows us that in the amazing world of proteins, sometimes even chaos has a purpose.